the talk herself. This is about the diffusion means and heat kernels on manifolds. And so I will briefly introduce the Fréchet mean again and the diffusion means. I will speak about the asymptotics and smeariness of the diffusion means and give some examples and applications to hopefully convince you that these diffusion means are actually worth looking into. So let's start. Again, the Fréchet mean on a Riemannian manifold with geodesic distance d. We define the population and sample Fréchet functions as the expected square distance or and the sum of square distances, respectively, and the population and sample Fréchet means are then the minimizers of these functions. And of course, the Fréchet mean reduces to the classical mean on a real vector space, right? This is a good property. So why use the Fréchet mean? So the first is that it satisfies the correspondence principle. So what's a reasonable mean on a manifold is not a priori clear. It should satisfy the principle that it reduces to the usual mean on Rm. Otherwise, we would probably discard it as a notion of mean. And on Rm, we have additional nice properties of the mean, namely that it's very nicely interpretable. It's a parameter value for many probability distributions. Especially, of course, the multivariate normal, but in one dimension, it's the exponential, the Bernoulli, the binomial distribution, you name it, right? So in terms of many probability distribution models, the mean has very nice interpretation. And on manifolds, this is not so simple. We don't have as many generic intrinsically defined distribution families on the manifold. One can often define something on, for example, a tangent space and then project it on the manifold and so on. But it would be nice kind of to look into intrinsically defined distributions. And one intrinsically defined distribution family that we are especially interested in is the isotropic Gaussian distribution defined via a Brownian motion. That one has two parameters, namely the diffusivity, which is just a real number, and a starting point, which has, of course, one could say it has m+1 dimension, m+1 parameters in an m-dimensional manifold. So to estimate this starting point, right, this p, the square distance that's used for the Fréchet mean is replaced by the negative logarithm of the heat kernel. And the heat kernel is the solution to the heat equation, where this delta here, this Laplace operator on a manifold, is the Laplace-Beltrami operator, which includes, of course, curvature terms. And we assume symmetry of the heat kernel in the first two arguments. All right, and then on a Riemannian manifold, with a heat kernel, we define the population and sample negative log likelihoods here as the expected value of the negative log of the heat kernel, or the minus the sum of the logs of the heat kernels. And the population and sample diffusion means are then defined as the minimizers of these likelihoods. And it turns out for real vector spaces, the heat kernels are just the normal likelihoods. And therefore, all the diffusion means for each diffusivity T are the same point because the normal likelihood, the two parameters decouple, right? So they satisfy the correspondence principle. And if we multiply by 2t, the minimization, of course, is not affected. And we can take the limit for t equal to going to 0 then. And it turns out that this negative log likelihood actually converges to the square of the distance. So we recover the Fréchet mean as the diffusion mean for diffusivity 0. So in a sense, the extreme low variance limit of the diffusion mean, okay? So this is also kind of nice. And now let's speak about asymptotics and smeariness. And I think I should hurry a little bit. So I again introduce the exponential map. This is a map from tangent space to the manifold, where a vector is mapped to the point on the manifold at the end of a geodesic segment, which starts in the direction of the tangent vector and has the same length as the tangent vector. So this red arrow here indicates this geodesic segment, and it's the same length as the blue vector in the tangent space. And we define the sample diffusion mean in tangent space just as the mapping to the tangent space of the population diffusion mean, okay? And we denote this by a nu to make clear when we are in tangent space and when we are on the manifold itself. And we can define a smeary diffusion mean, just like the smeary Fréchet mean, if the likelihood at its minimum is flatter than a normal square parabola. We speak of smeariness, and then it turns out that the asymptotic rate of the diffusion mean is actually slower than square root of n. Okay, so, and the limiting distribution is not a normal distribution, but a somewhat related distribution. And we can also to deal with finite sample smeariness, we can define the variance modulation as the quotient of the variance of the sample diffusion means rescaled by n, so that it would actually, for a standard central limit theorem, just compensate for the asymptotic rate, divided by the variance of the random variable itself. And if this modulation, this variance modulation, has a supremum which is larger than 1 but finite, we speak of finite sample smeariness. And now, as I said, diffusion means can be interpreted in the framework of generalized Fréchet means, and there is a lot of asymptotic theory available there. So all the central limit theorem requirements are actually satisfied for diffusion means on spheres. And this is just referring to the general central limit theorem. So what it turns out that a property which actually, so if we have a Taylor expansion or a power law expansion of the likelihood near the population mean with order R, where R might be larger than 2, then we get a normal square root of n rate for the sample mean times its absolute value to the power of R minus 2. So if R is equal to 2, we get the standard central limit theorem. If R is, for example, equal to 4, we have essentially a third order term here, signed third order component wise in this vector. And that will converge to a normal distribution, which means, of course, that this sample mean itself will not be normally distributed, and that its asymptotic rate here will be slower, okay? Namely, as written here, 1 over 2 times R minus 2, 1. Okay, now let's look at some examples. On the circle, the heat kernel is the wrapped normal distribution. So again, a well-known distribution, but it turns out here, if we look at the likelihood, that the parameters do not decouple. So the diffusion, the mean, actually depends on T, on the diffusivity, right? And this is actually for manifolds a very typical feature. As you recall, for the Euclidean vector spaces, they decouple. For manifolds, they don't. And even on the circle, they don't. And for spheres, it's of higher dimension. We can use Gegenbauer polynomials to write out a series expansion of the heat kernel. And again, we have this problem that the diffusion mean depends on diffusivity, or well, this property. It's not a problem, it's a property. And also, it turns out that in these sequences here in this series, the terms with higher k become smaller very quickly, exponentially actually, in both cases. So in both cases, it's usually enough to look at the first 5 to 10 summons of the sum to get very, very accurate estimates, okay? So this is also numerically very easily tractable is what I mean. And here is an example, namely a classic sea turtle data set where 76 sea turtles leaving their nests after egg laying were observed in which direction they were going. And as you can see here in the histogram, most went towards the east, which is where the rising sun is and the beach, and some get lost and move inland, right? And so we have a bimodal distribution. And it turns out if we look at the Fréchet mean, so for t equal to 0, here the blue curve, this is the Fréchet function now, or the likelihood, if you will. This has a very flat minimum, and the dot here is actually denotes the minimum position. And if we go up with the diffusivity, this minimum here becomes rounder. It's actually closer to a square root, to a square approximation. And actually the diffusion mean here approaches actually the middle of the main mode. And if we look at the modulation, the variance modulation here, we see that the more we increase our diffusivity, the more our modulation drops. And it turns out if we estimate the diffusivity for this data set, we get roughly 1, so 0.96. So this curve here is actually kind of the best estimate for both parameters for the diffusion mean. And it's fairly flat, so it mitigates this effect of finite sample smeariness. And this is actually a generic property of the diffusion means. And the second example is geomagnetic pole positions from rocks, where you can determine the North Pole position in the past from magnetic rocks. And there are periods which you probably know, the magnetic poles of the Earth switch every few 100,000 years. And if these rocks were emitted from a volcano during such a period, some will show the old pole direction and some will show the new pole direction. And then in such a rock sample, you get a distribution like this for the North Pole position, right? And here it turns out, again, from a large set of such samples, many exhibit finite sample smeariness. And if we take diffusion means here, we see that this finite sample smeariness is mitigated for these data sets. So I think the diffusion means have very nice properties. They are fairly easily calculable. In many manifolds, there are closed form expressions for the heat kernel, and there are also generic series expansions so that you can fairly easily compute the first few terms. The terms usually decay very quickly, so just a few terms will give you usually good numerical results, and they mitigate some of the problems that can arise in positively curved manifolds. And therefore, I think diffusion means are worth looking into. And the larger paper here is again on the archive if you want to have a look at this. Thank you.
Do we have any questions in the room? So, yeah.
So you advocate for using the diffusion mean, and in the case where you have no closed form solution,
yes,
for anything that you, for example, for the Fréchet mean, you need to use another iterative algorithm.
Yes.
What is possible to do in the case of diffusion to estimate?
Yeah, one also uses a numerical method for the minimization, but it works pretty well. I mean, as with the Fréchet mean, it has similarly good performance. Actually, in this case, it turned out it seemed to be even more robust to running into local minima. And maybe this can already be a kind of guessed from these functions here. The higher the diffusivity is, the kind of the less jagged these functions become. And so in a sense, it seems like it's less likely to run into local minima because there are less, apparently. Because what turned out is we did this thing with 10 repetitions, but for the diffusion means, if we didn't do the 10 repetitions, but only just ran every minimization, numerical minimization once, we got almost exactly the same results. I mean, tiny numerical variation only. So it looks like there we didn't actually need that in these real applications. Somehow the problem of local minima in the minimization is apparently even mitigated typically.
So can I ask you another question? Okay. So if you take a Brownian motion on a sphere, yes, the same holds for compact Lie groups. But if you take a Brownian motion on a sphere and then take its expectation at time t as a vector, it's a vector on a sphere. Take the expectation. the length is exponential minus the time, and the direction, the unit vector, is the starting point. Therefore, it's very, very easy to separate the time which you're using as a variance and the starting point which you're using as a mean. It's not maximum likelihood or anything. It's a kind of method of moments, but it's very, very easy to separate, to estimate them and separate them right away.
Right. Yeah. Sure. I mean, these spaces are probably. I mean, these are very symmetric spaces I showed as an example, and those are probably not the best examples for this problem I mentioned. Yes, I think I agree.
So, any more questions?
Can you explain what you mean by smeariness? How limited the problem?
Oh yeah, I glossed over that pretty quickly. So smeariness means that in the central limit theorem, right, you have square root of n times the distance between sample mean and population mean is asymptotically normally distributed. So the convergence rate, basically statistically, right, in distribution for the sample mean to the population mean is square root of n, if you will, or 1 over square root of n. And smeariness actually means that this convergence rate is slower. So for example, 1 over n to the 6, it could be 1 over n to the 1/6, so 6th root. And 6th root is obviously very, very much slower. So you need much higher sample sizes, for example, to be really close to this population mean. And also the asymptotic distribution of the sample means is not normal, but it's derived from a normal distribution, and actually turns out it's multimodal. So it's also kind of an unfortunate limiting distribution. Yeah, and this is kind of a problem that turns up fairly generically on positively curved manifolds to some degree.
All right. So can you maybe look up the discussion?
Oh,
yeah.
Sorry.
No problems. There's nothing? Okay, good.
Okay. All right.
So let's thank Benjamin once more.
Yeah.